All right, in this video, we summarize the different kinds of integrals that we've looked at so far in the context of the kinds of integrals that we are going to see in the very near future. So in this video, we transition essentially from line integrals to surface integrals. Okay, so what we're seeing in this first pane of formulas is our first line integral of our scalar function. F was a scalar function. Okay, and we knew the definition of that was given by what you can see here. Okay, so we need to evaluate the function along the curve, and it's very important to note that this ds notation, ds is equal to the magnitude of the velocity dt. So that was a notation that became important. So specifically, there was a special case that when the scalar function was 1, that we integrated 1 ds, that became the arc length of the curve c. So the special case of the scalar function line integral was an arc length integral. Okay, and then we moved on to a new kind of integral called a work integral, and this was a line integral of a vector field along a curve C. And its notation and definition is given by this formula here, which means that we need to evaluate the vector field along the curve and then do the dot product with the velocity of the curve r prime. Okay, and then a slight rewriting of r prime right here. If you divide by the magnitude and multiply by the magnitude of the vector, you've essentially multiplied by you've multiplied by 1. And we can see that from a prior section that r prime divided by the magnitude of r prime is what we call the unit tangent vector. And here we can see the magnitude of r prime dt occurring, which is ds, the arc length, the length element. So we can see here that the line integrals, if we're looking at sort of a pattern that's going on, that a line integral of a vector field can be rewritten in terms of the ds notation from the line integral of a scalar function if we take the vector field, dot product it with the unit tangent vector, and then integrate with respect to the arc length element ds. Okay, and that led us to a work integral that we could also use the fundamental theorem of line integrals on if the vector field was the gradient of a potential function phi. Then we had the fundamental theorem of line integrals, which would kick in and make these line integrals of vector functions, vector fields, quite a bit easier. Okay, so that's where we've come from with the line integrals. What we're going to see is something very similar happen with when we move to surface integrals. And I just want to point out for these line integrals that the key idea is that we had to come up with a parametric description of the curve C. Okay, you can see everywhere that we have the curve, the derivative of the curve, and that is showing up everywhere. T, the unit tangent vector, is the velocity divided by the magnitude of the velocity. So it is this parametric form of the curve that gets line integrals going. Okay, so as we move to surface integrals, we'll see something similar happen. Okay, there are two kinds of surface integrals that we'll see. Right here we have a surface integral of a scalar function, just like we did for line integrals. There's a scalar function, and we have a new notation d sigma, and the actual meaning of this integral is that we need to find the scalar function, and the key idea here is we need this parametric form r of u comma v is a parametric form of the surface. Okay, and once you have that parametric form of the surface, you can compute the partial derivatives of that function. You can do the cross product of those vectors, and then you can find the length of that vector. Okay, and it's this RU cross RV du dv right here. This is what we're denoting as d sigma. Okay. And what we're going to find is something interesting that happens, that if there's a special case that if you let the function that you're integrating equal to 1, when you integrate 1 d sigma by itself is the magnitude of RU cross RV du dv. What we're going to find is that this will be the equivalent of the length of the curve. This will be the equivalent of the surface area of the region R. So a scalar, a surface integral of a scalar function, when that function is equal to 1, a special surface integral is a surface area integral. Okay, and then we will see, because just like in the line integral case, we can do surface integrals. Both of these are examples of surface integrals. Okay, that when the vector field, we now have a vector field, right? And we're integrating over some part of a surface, right? We have this dot product that comes into play right here. And so we have to find the vector field along the surface. We need to dot product with RU cross RV. Okay, we'll discuss the significance of that in a little bit. But we have the same trick that we had in the line integral case, that when you divide by the magnitude of RU cross RV, right, we're seeing the d sigma notation appear from the scalar case. So RU cross RV du dv, that's what we call d sigma. And RU cross RV divided by the magnitude of RU cross RV, this is what we're going to end up calling the unit normal vector to a surface. Okay, and then we have the vector field along that surface. So these kinds of integrals, surface integrals of vector fields, are what are called flux integrals. Okay, and what we can see if we zoom back out and you look at the patterns that are forming, we can see the comparison favorably to line integrals and surface integrals with respect to each other. So in future videos, we will need to transition into surface integrals, and the key, just as it was in the line integral case where you had to compute the parametric form of the curve, what will be key in the surface integral section is that we will have to come up with a parametric form of the surface. And once you have that parametric form of the surface, we'll take derivatives with partial derivatives. We'll need cross products and magnitudes of those cross products. Okay, so surface integrals, the key part is a parametric form, a description of that surface. And that is what we will begin doing in section 16.5, the parametric form of surfaces. And then we will transition in later videos to special surface integrals, one of them being the surface area integral. And then we will move on to flux integrals. So that is an overview of where we're going. I hope it helps a little bit and kind of just get some of the notation set and how it might parallel the line integral case.